welcome everybody. My name is Chris Corcoran. I'm a professor of mathematics and statistics at Utah State University. I have been at Utah State now for 15 years, but still work closely with colleagues at Cytel Software Corporation. When I was a graduate student, my advisor was Cyrus Mehta, who's one of the founders of Cytel Software, and so I've continued my collaborations with him since leaving Boston and coming back to Utah State. I am going to be talking today about a new module in StatXact that performs permutation and exact tests for correlated data. So this is quite a significant addition to StatXact, and what I'm going to do is I'm going to share a little bit of the rationale behind the exact test that we've developed. And some of this might be a little bit of review for those of you who are more experienced. For others, it may be just a reminder about how exact tests work. But I'll share that rationale with you, step through that. That'll probably take about 15 or 20 minutes. And then we'll do some examples in StatXact using these new tools. So let me go ahead and start here. I've put not only my own name, but also the name of Pralay Chowdhury at Cytel Software Corporation. He's one of my close collaborators and also the Vice President for Research and Development at Cytel. I've worked closely with him on this project. And I should also acknowledge that a lot of this work has been supported through small business innovation and research grants from the NIH. As I said, I'm from Utah State. For those of you who don't know where Utah State University is, we are in northern Utah, up by the Idaho border, a little bit off the beaten path, surrounded by mountains. And even though I can't see any of you, I thought you might like to know at least what it looks like around my environment. This is more or less kind of the view from my office. So this is what I look at every day. I'd welcome you to certainly welcome you to visit me sometime if you want to enjoy the surroundings here in northern Utah. Now, just to motivate what we're talking about today with a few examples, I'm going to introduce a few data sets that we'll analyze later, but I'm going to use these to illustrate why issues in exact testing and correlated data often arise in public health research and epidemiology, clinical trials, and so on. These are all actual data sets that we have gleaned from through our contacts with other researchers that we work with just from day to day and have contacts with. This particular data set is a series from 9 children who had a congenital defect that's referred to as congenital hereditary endothelial dystrophy. Now, this congenital problem leads eventually to lazy eye, and one way of combating this or treating this is by performing corneal grafts. So what you're seeing in this table is you're seeing this series of 9 children categorized according to age. We have those who were younger than 3 years, those who were older, and the ratios or the proportions that you see there represent the number of grafts that were rejected out of the number of grafts that were performed on each child. So you can see that that 7 of the children had 2 corneal grafts, and 2 of the children in the older age group actually only had 1 each. You can also see that all of the rejections occurred in the older age group. And so in terms of trying to assess whether or not there's any association between age and rejection rate, there are 2 issues. One is that since all of the rejections occurred in the older age group, it's hard to, compute something like, say, an odds ratio or something along those lines when either the numerator or the denominator is going to be 0. We're not going to be able to do inference. But aside from that, there's also the issue of correlation within child. In other words, the 2 eyes for each child are correlated. In other words, knowledge about rejection in one gives you information about rejection in the other. And so somehow we have to account for that dependency between eyes also in doing some sort of a hypothesis test or any other inference. So in other words, this is problematic. In fact, in the article that was published that included these data originally, the authors lamented the fact that they could not do any inference because all of the rejections occurred in one group and they didn't know how to handle the correlation. So the tools that we're talking about today help us to be able to analyze data such as these. Now, you can see the rejection rate overall, if we just collapse over eyes, is 0% in the younger group and 50% in the older group. But the question is this evidence that there's an association between a higher rejection rate and older age? So that's the research question. Now, the next data set is from a multi-center clinical trial. This was a trial for a drug that was developed to treat pain. And so this is a fairly typical setup in terms of multi-site trials. You can see that within each site there were a certain number of treated patients, a certain number of patients who were given placebo, and then we have recorded here the number of patients within each group for each site who actually experienced pain. Again, if we collapse over all of these sites, in the treatment group, 2.4% of all of the patients across all sites experienced pain, whereas about 11% among the controls did. And so again, the question is there evidence here that that treatment actually leads or is associated with lower pain rate? But also, as you know, we have to somehow account for site. In other words, the individuals within site are going to be likely more similar than individuals between sites. So somehow, again, that correlation needs to be accounted for in the analysis. Here are data from a developmental toxicology study. So there were 4 litters per dose, or 4 impregnated mice per dose, who then were after being exposed to this toxic substance, they were sacrificed and their litters were examined to see how many of the fetuses within each litter, excuse me, were observed with either no malformation or just a slight malformation or severe malformation or death. Again, if we collapse over these dose groups, you can see that it appears, at least we observe, that the proportions within each of these malformation categories appear to differ across these dose groups. The question is there evidence that dose actually corresponds to a difference in these proportions, a significant difference? But again, the fetuses within each litter are going to be more alike than fetuses across litters. And so again, we have to answer these research questions while accounting for the correlation. Now again, the low proportions in some of these categories, particularly in the last, make this data set fairly sparse, and so we may be a little bit nervous about using some sort of large sample approximation to analyze these data. It would be nice to have some sort of categorical data method that would give us an exact p-value in this case where we observe a lot of zeros or a lot of imbalance in the overall table. Now, just to go back a couple of steps so that we can understand what the rationale is for the exact test that we've created for correlated data, I just want to go back and quickly review Fisher's exact test. And again, for some of you, this may be old hat. For others, this may be a nice reminder of where this test comes from. But Fisher's exact test is a test that's commonly used in data analysis that does not rely upon any large sample approximations like a chi-square or any kind of normal approximation. And it's very useful in cases where the table is very sparse or the overall sample size is small. Where does this come from? Well, the fundamental question has to do with what we call the hypergeometric distribution. So in other words, if I present you with this bin that contains some red balls and some black, here in this bin specifically we see 5 black and 6 red, and I ask you to reach into this bin and pull out 4 balls, the question here is, what's the probability that 2 of those will be red? Well, there are 11 balls total, and so that gives us 11 choose 4 ways of selecting 4 balls at random from 11, where the order of our selection doesn't matter. And this is what gives rise to what we know as the hypergeometric distribution. Of all of those possibilities, there are 6 choose 2 ways of choosing 2 balls from the red, and 5 choose 2 ways of choosing 2 balls from the black. So this equation down at the bottom gives us the probability that out of a sample of size 4, we select exactly 2 red. By the way, I just noticed here there's a little typo here. That should be a 2. So I apologize for that, but it should be 6 choose 2 times 5 choose 2 over 11 choose 4. But that's an easy probability to compute and something that is often taught in introductory statistics classes. And I'm not going to spend a lot of time on this next slide, but in general, we can come up with a formula like as we did on the previous slide, but do it for just kind of a general number of black balls, a general number of red, and just some arbitrary sample size that we select. Well, what does this have to do with exact tests and what we're talking about today? Well, there's the famous story that gave rise to Fisher's exact test is that Fisher had a colleague who claimed that she could tell whether or not when she tasted a cup of tea, whether the tea had been added to the cup first or the milk had been added first when the tea was prepared. So Fisher, being a scientist and a natural skeptic, proposed an experiment where he said, okay, well, here are 8 cups of tea. I've prepared 4 of them with tea first and 4 with milk first, and now I'm going to randomly order these cups and have this woman drink each one at a time, and she's going to guess which 4 are tea first and which 4 are milk first. And the question is, okay, well, if once she actually tastes these cups and makes her guesses, how convincing would that be in terms of the result? In other words, if she picked all 4 correctly of the tea first cups, would that provide evidence for us personally that she knew what she was talking about? Or only 3? Would that provide evidence? Well, it's easy to compute a probability for this using that hypergeometric distribution that we talked about by organizing the data in a 2-by-2 table. And this table that you see on this slide is just one hypothetical outcome of this experiment, where she correctly guesses 3 out of the 4 tea first cups. And the question is, well, what's the probability of this? Well, assuming she doesn't know what she's talking about and she can't identify tea or milk first cups in the way that she claimed, then really this is just a bag of red and black balls. So all she's really doing is she's choosing 4 balls at random, and picking 3 out of the first correctly is like picking 3 out of 4 red balls from a bag of 8 just by chance. And so using that hypergeometric distribution that we talked about in the previous slide, that allows us to compute a probability. In fact, it allows us to compute probabilities for all 5 possible outcomes of this experiment. So each one of these is one of the 5 potential outcomes, and each one has an associated probability based on that hypergeometric distribution. So in other words, if she were to pick 3 out of 4 correctly, you can see that the probability of that is about 23%. So that's not all that convincing, really, because you can phrase the question like this. If we're going to think of this in terms of a p-value, then the probability under the hypothesis or the setting that she doesn't know how to distinguish these cups, the probability that she would do as well or better than 3 correct guesses is just the sum of these two tail probabilities, so about 23% plus about 1.5%. In other words, there's about a 24.3% chance that she would be able to pick 3 correctly or better at random. So that's not all that convincing. By the way, I guess the punchline to the story is it actually turned out in real life that she picked 4 out of 4, which I think most of us would argue would be fairly convincing. But nevertheless, that's how the exact p-value is computed. And in general, that's how exact p-values are computed for just any contingency tables. That argument has been extended to, it was extended after Fisher to just tables with arbitrary numbers of rows and columns. And but the fundamental argument is that if you condition on the row totals and the margin totals, as we did with that tea tasting example, then that allows you to derive a distribution for which these exact probabilities can be computed under a null hypothesis that the row columns and the row variable and the column variable are not associated. So that's the underlying rationale for these conditional exact tests, is that we freeze the row margins, we freeze the column margins, and that allows us to compute these hypergeometric probabilities. Now for correlated data, so now moving ahead to this new module in StatXact, what is the argument that we use, or what's the rationale that we use for exact tests for correlated data? Well, it's a similar rationale. We also condition on margins of tables, but in addition to that, we have to condition on another statistic that contains information about the correlation within these clusters or these sites or individuals in our study who have more than one measure, whatever it may be. Now, how does that work? I think that, in a setting like this, in a webinar, it's very hard for us to be highly technical, to throw a lot of formulas, on these slides. And so as opposed to trying to, show you some of the mathematics behind it, I just want to illustrate for you how this works so that you at least understand where these exact p-values are coming from. Now let's go back to the Corneal graph data example. You can see that I'm representing these data now in a slightly different way than you saw on that original slide where I presented this example. Here, each column in this table corresponds to a child in the study. Now, the column margins tell you how many grafts were performed on each child. So you can see there were 7 children with 2 grafts and 2 children with 1. And I've coded what we might term as the treatment or exposure as either 0 or 1. 0 for those children who are younger than 3, and 1 for the children who are older than 3. And then for each child you see is recorded the number of rejections. So on the row margins, 4, that represents the total number of rejections. And as with the exact test for uncorrelated data, like Fisher's exact test that we just talked about, we condition on these margins. So in other words, we condition on all of the column margins. And we also condition on the number of individuals in the sample who experienced or the number of eyes with a rejection. So that's why I'm circling this 4. So far, this looks similar to any two-way table that we might analyze, and we're still conditioning on the margins. But what are we doing in addition to that allows us to account for the correlation between eyes? Well, we have other statistic, this statistic here represents the extra statistic that I alluded to on the previous slide that allows us to account for the correlation. So in addition to, freezing the margins of this table, the column and the row margins, we also consider this statistic. Now, what is this statistic? It turns out it's the sum over all of the children of the product of the number of rejections for each child times the number of no rejections. So, so I'll just step through this. For the first child, the number of rejections is 0. The number of no rejections is 2. And so that child's contribution to that correlation statistic is 0 times 2. And likewise for the second child and the third. And we continue summing over all of these children to compute a statistic, in this case 2, that represents some information about the degree of correlation between eyes within child. Now the test statistic, this looks like what we would refer to as a linear rank test statistic or a trend test statistic for any two-way table. In other words, it's just the product of the number of responses times the exposure, so the exposure variable. So for the first child, they're in group 0, and they have 0 rejections, and so their contribution to the test statistic is 0 times 0, and so on. So in the end, the correlation statistic is 2, the test statistic is 4, and so these 3 statistics that I've circled here, these are the 3 critical statistics with respect to computing an exact p-value for these data. Now again, how does this work? Well, here's our observed table. Okay, we have the row margin, which is 4. That's the number of total rejections. We have this correlation statistic, which is 2. And then we have our test statistic, which is 4. So how do we proceed with an exact test? Well, as with the t-tasting experiment, what we do is we consider all possible tables of the kind that you see at the top of the slide, the observed table, that also give us these values for the 2 statistics U0 and UC. So for example, here's a table, and I've dropped the margins. I'm just including the rows just for the sake of illustration. But here's one table that gives us a number of rejections equal to 4, as with the observed table. But you can see that the correlation statistic is equal to 0, which is not equal to the observed correlation statistic. And so in other words, that's not a table in the reference set. So that's not a table we consider for computing the exact p-value. Now here's another table. This table also gives us a number of rejections equal to 4 across all these kids, but in this case, the correlation statistic is equal to 2, which is the same as the observed table. So this table is in the reference set. So the way that we compute the exact p-value is we circulate through all of these tables. We find all tables with cell values that give us the same values for these 2 statistics that we observed for the observed data. And then we order them according to their test statistic. We order them according to this test statistic here that I'm circling with the cursor, this t equals 4. So this is the value of the test statistic for the observed table, and you can quickly do some arithmetic across this table at the bottom to compute what the test statistic is in that case. You can see that it's actually equal to 0. So in other words, we take all the tables in this reference set, we arrange them according to these statistics, and then we compute a tail probability just as we did with the t-tasting experiment. So in other words, the p-value is going to be the sum of the probabilities of all tables in this reference set that give us a value of t that's greater than or equal to 4. So in other words, the bottom line here is that what we've accomplished is we've been able to derive a rationale for computing exact tests, exact p-values for tables that have correlated data. So again, the way that this works is that given a particular setting or given a certain study design, you determine the appropriate test statistic. Given this representation, we condition on the margins of the table and also an extra statistic that represents the correlation. Then we order the tables in this set of tables according to their values of this test statistic, and then we compute the tail probability just using this hypergeometric distribution argument. And so now the module in StatXact contains analogs for all of the standard tests that we use for tabular data. So in other words, there's a trend test, which can also be stratified. There's a test for two ordered multinomials. And by the way, I'm going to step through examples for each of these over these last 10, 15 minutes of my presentation. There's also a correlated data version of Fisher's exact test and the chi-square test that we would use for R by C tables. We have an exact test for a singly ordered R by C table where the rows are ordered but not the columns. We have a test where the rows and columns are both ordered, so a linear bilinear association test, and also a test for stratified 2x2 tables. And in addition to those, an exact test that actually helps us to measure the evidence for or against clustering within the individual units that we feel may contain correlated observations. And in addition to that, there's a multivariate trend test. So in other words, you can think of this as a kind of a Cochran-Armitage trend test where we have multiple outcomes, not just one. These are all contained now in a correlated data module in StatXact. So let's go back to this example here. The question is there a significantly higher rejection rate among older children with CHED, and can we compute an exact p-value, and also can we do that accounting for the correlation? Well, using these tools now that I've just sketched out, now we are able to compute a p-value of this association. I'm going to toggle back and forth to StatXact for some of these examples. So here in StatXact, I've already opened up many of these data sets just to save us some time, but here is the data set that represents the data from the Corneal Graft example. So you can see we actually have 16 observations because the rows here represent individual eyes. The first variable is subject, which represents the child. So these two rows correspond to the two eyes that receive corneal grafts for the first child. The next variable tells us whether or not each of those eyes was rejected. So that's going to be 0 if it was not rejected and 1 if it was. And then the last variable for each eye tells us which age group the corresponding child was in. So these first 8 eyes correspond to the first 4 children who are all younger than 3. Okay. Now here, just to illustrate, some of these results I've already computed because for a few of these examples it takes, it may take 30 seconds to obtain an answer because exact tests are very computationally intensive. And so I didn't want to just sit here and let it run, but this one runs fairly rapidly. So let me show you how this works in StatXact. You can see that all of the correlated data tests now are under this heading, Inference for Correlated Categorical Data. Here we have 2 binomial populations. In other words, we have two groups of children, one who are younger, one who is younger than 3, one older than 3. And so we want to compare these 2 age groups. And so we're basically doing a trend test, but with only 2 groups. So rejected, that's the response. Age group, that's the explanatory factor here. And then the cluster ID is subject, which identifies the child. We want to compute an exact p-value. Now when I click OK, you can see here I get a result. Actually, the two-sided p-value it's 0.04762. So in other words, for these data, there is some evidence that that there is an association between age and rejection rate, that those who are in the older group have a significantly higher rejection rate. Actually, it's interesting. I spoke to one of the authors of the paper from which we gleaned these data, and she was very interested in this result because this disease, the CHED, is actually quite rare. And so most of the data sets that they work with are series that look similar to the one we're looking at here, where there are relatively few children and sample sizes are small. And so this was very interesting to this individual that we were able to actually conduct an analysis. Now let me go back and let's look at a few other examples. Moving on to the next example, this is the multi-site pain trial that we talked about here, where we want to compare treatment to control in terms of the rates of pain after treatment. But we want to, again, the key is that we want to control for site. And so here, I've opened these data here in this window. And this test for these individuals actually takes a little bit more time. If I were going to run it from scratch right now, I've already actually run the test and obtained the result. But if I were going to run it from here, again, I'd want to compare these two groups, treatment versus control. So in other words, treatment here is the explanatory variable, and the response is whether or not the individual experienced pain. The cluster ID is site, but here I also have a frequency count just because the data are displayed here in grouped form. But let's just go straight to the result, and you can see the two-sided p-value here. Is shown on this side of the screen. So about on the order of 10 to the -8. So very strong evidence here of a treatment effect, having accounted for correlation within site, which is the key. You know, there's very high imbalance here. The data are relatively sparse because there were very few patients among over 500 in the treatment group who experienced pain, only about 2%. And so, you know, the option of an exact test is actually quite useful for data like these, where the investigator may be a little bit nervous about using a large sample approximation where they observe so many adverse events among one of these groups. Okay, so going to the next example. Now here, as opposed to comparing binomials, so in other words, different treatment groups where the outcome was, you know, either, you know, pain or no pain or rejection or no rejection, here we have an outcome that is that actually has 3 levels. So this is a multi-center clinical trial again for people who are experiencing spasms and pain, I believe. And the 3 classifications of outcome here were either the patient experienced worsening symptoms or no improvement, or slight improvement, or a major improvement or a cure. So it's a little more refined. It's a little more refined scale in terms of the outcome. Now, 7 different investigators recruited subjects for the study. So the first investigator recruited 7 subjects. Those are the subjects that are here under treatment. Each investigator recruited subjects, and all of the subjects were either randomized to treatment or control. So this first investigator recruited 7 patients, all of whom were treated. 2 of those patients showed actually worsening of symptoms or had no improvement. One of those patients showed a slight improvement, and the 4 patients here represent those who had a major improvement or a cure. So overall, across all 7 of these sites, we can see what the proportions are, relatively speaking, across these different categories of outcome. And so the question is there evidence that the distribution of these response categories differs by treatment group? But more specifically, because these outcomes are ordered, in other worsening symptoms to slight improvement to major improvement or cure, we might also want some sort of, to measure whether or not that shift is ordinal. So in other words, we might want to specifically test whether or not the median response level is higher among those who were treated than those in the control group. And ordinarily, we would do that using some sort of like Wilcoxon test. But here, the key is that because the individuals within site are likely correlated, we have to account for that as well. Well, now in StatXact in the correlated data module, you can carry out a Wilcoxon test for clustered data, and I've done that here. Here, actually, I apologize. I actually forgot to open this particular data set up before we started, but during the question period, I'll open this up to avoid wasting a lot of time. But I'll show you that under the non-parametric menu, that inference for correlated categorical data, it also includes methods for 2 ordered multinomials, which is what we have here. And we can select the Wilcoxon rank sum test, or we can use a few other tests that are available for independent data as well. But that allows us to carry out a Wilcoxon test for the example that I just showed you. Now, moving on to the next example, this is the analog to an R by C table. In fact, what we have here is basically a 3 by 4 table with clustering. Now, you may wonder why I'm saying it's 3 by 4, because we actually have 4 rows in the table. But note that the number of categories for the outcome is equal to 3. So the frequencies that are in parentheses within each row, down each column, these again represent individuals who are in the study, but this is a developmental toxicology study. This is the one that we talked about earlier, where these 4 litters of mice were randomized to these doses of the toxic material, and then they were evaluated afterward for their levels of malformation. So this first litter here in the dose group of 0, this represents a litter of 8 mice, 7 of whom were observed with no malformation, 0 that had slight malformation, or 1 with a severe malformation. And likewise, there are 4 litters per dose that were each observed after the experiment was conducted. And these percentages on the bottom represent the percentages across these response categories in aggregate. But again, if we were to ignore litter, so if we were not to pay any attention to the litters that these mice came from and treat them all as independent, these data would be stored in a 3 by 4 table. In other words, there'd be 3 rows representing the different response categories for malformation, and then 4 levels of dose. And one might, carry out a chi-square test or a Fisher's exact test or something to assess that association. But we, in this case, have to appropriately account for the correlation within litter between these subjects. But there's some additional considerations here with this example. The dose is ordered and the response categories are ordered as well. So we can consider different approaches for a two-way table. We may carry out a chi-square test or a Fisher's exact test where we consider these the dose variable and the outcome variable to be unordered, or we could just take into account just the ordering of the column variable, or we can consider this ordering to be two-way. So in other words, we can carry out a test where we specifically examine the alternative hypothesis that there's a linear association. In other words, the higher the dose, the higher the median malformation level. So we can carry out all three of those types of tests in the StatXact module. To illustrate, let's go to this example. Here, this represents the data by litter. So in other words, these first three rows represent counts from the first litter corresponding to these different outcome levels. So here's the dose for that particular litter. Here are the outcome levels: no malformation, slight malformation, or severe malformation or death. And here are the number of animals within that litter within each of those three categories. Now I've carried out a chi-square test. The way that we would do that in this menu is that we would select unordered R by C table. So we're not assuming any ordering of the outcome variable or the response variable, and just select the Pearson chi-square test, and you can see that I put the values of these variables in the appropriate places. I'm going to cancel out of this because, again, it takes about 30 seconds to a minute to run this test. But here is the result. The two-sided p-value is about 0.001. So in other words, there's very strong evidence of an association between dose level and the distribution of malformations, and that's taking into account, again, the clustering within litter. Now, what about ordering? What if we allow ordering within the response variable? So we want to know whether or not dose level is associated with higher median malformation level. That's what the Kruskal-Wallis test helps us to test. And here's the result for that test. If I want to carry out the Kruskal-Wallis test, again, I just go to singly ordered R by C table, and I can pick one of these options, of which Kruskal-Wallis is one. Fill in the appropriate variable names. I'm going to cancel out of this because, again, I've already carried out this test, and there is evidence of that kind of association. And finally, the last question is whether or not I can treat this as a doubly ordered table. So in other words, there's some evidence of a linear association between dose level and median malformation level. And that's the linear by linear test. To carry that out, again, I go under this menu and choose doubly ordered R by C table, select linear by linear association, fill in the appropriate variables here in the dialog box, and the result is a two-sided p-value of about 0.003. So there is evidence of a linear correlation between dose and malformation level. Now, finally, just to finish up here before we go to questions, I should also point out that aside from these tests for two-way tables, there are also a couple of other interesting tests in StatXact for correlated data. One is a test that the data are actually correlated, or it's a test for evidence of clustering. For example, here are some data from 30 brain tumor patients. And for each patient, there were 5 histological events that were measured, and you can see that some of these patients, some of these patients experienced 4 out of 5, 5 out of 5, 4, and so on. But the question is whether there's evidence of clustering within patient with respect to these histological events. So can we compute a p-value that there is within patient correlation? Now in StatXact, that's really easy to do. Here are the data. You can see that for each subject, we have 5 different outcomes, one corresponding to each histological event that was measured, and then whether or not that was observed for that particular patient. And to get a test of clustering, we select test for correlation under the binomial populations. We identify the cluster ID, what the response variable is, and then we carry out the test. And you can see here, based on this two-sided p-value of about 0.015, there is evidence for these individuals of clustering within subject. So that's something that that can be somewhat useful in some settings. And then finally, I alluded to this earlier, but there is a trend test as well available for multiple outcomes. Now, these data here, the data are contained in the examples that come with the StatXact package, but the data here as they're presented in this table are actually collapsed. So in other words, the different symptoms for each animal are not actually mutually exclusive, and there were 8 animals per dose. So this first column is telling you that across these 3 symptoms, there were 4 animals out of 8 experiencing the first, 2 experiencing the second, and 4 experiencing the third. And some of them may have been the same animals, but all I'm doing is collapsing here just for the sake of convenience. But the question is there a trend across all 3 symptoms? Can we test that simultaneously? In other words, you can think of this as a multivariate Corcoran-Armitage trend test, where you're actually carrying out a trend test across these 3 symptoms at the same time. And that's also available in StatXact. Here are the data here. They have to be tabulated in a certain way in StatXact, but once they are, it's fairly easy to obtain the p-value. Of course, we go under multiple binary outcomes, test for trend. We choose the exact test. And I'm going to cancel that because, again, I've already computed this. But the result is a p-value of about 0.002. So in other words, there is evidence of, a trend across these 3 symptoms simultaneously. Of course, that kind of multivariate trend test is very useful, especially in developmental toxicology, where the researchers may be measuring, more than one thing. All right, and that's it for that part of the presentation. We're going to invite questions now, moderated by Mike Weitz from Cytel. But here are the email addresses for myself and also Prolase and Chowdhury at Cytel. You're welcome to email us questions outside of this session. Also, at Cytel, the StatXact contact is Andrea McSweeney. She handles, questions about licensing and procurement and so on. So she can also be contacted. So with that, I'll turn the time over to Mike.
Hi, Chris, and thank you very much. And hello to today's online audience. This is Mike Weitz. I lead the marketing efforts here, and I'm speaking from Cambridge, Mass. today. First of all, would like to thank everyone for joining us, and we're going to get right into the questions and answers. Again, you can submit your questions to Chris in the question and answer panel that you have on your WebEx screen. While Chris is preparing, taking a look at those questions, including the first one I see from Dave Whiteman, I'd like to remind you of a couple of things quickly. Today's slides, as I noted posted in the question and answers panel, are available right now from our website. Simply go to cytel.com, look for the Software Solutions tab at the very top left, and it'll take you to our StatXact page, and you'll see the download slides link prominently displayed on the StatXact page. We will also, in 2 to 3 days, everyone attending, in fact, everyone who registered today will be emailed a repeat of that link. And also, we're going to make the data sets from today available as well as text files for download as well. You can use those text files as you wish. You can try them in your version of StatXact, and if you're not a StatXact user, you can give it a try in your other statistical application. We welcome that. As well, that email will contain a link for a replay, a free replay of today's webinar with Chris that will be posted to YouTube when it's made available. So again, everyone will be receiving that email. So stay with us, please, as Chris prepares answers. We will also, at the very end, when Chris has finished your questions, we will be very happy to, if you stay with us, because at the conclusion, you'll be directed automatically to a very brief survey, which is very useful to Chris and the software development team, who are very keen to learn your comments and ideas regarding exact statistics and especially future developments of StatXact. My last reminder is we also will have an email that will go to everyone with a special pricing offer for StatXact, or either commercial license or academic licenses for the newest version of StatXact 10. But as you can see on the slide, don't hesitate to contact our Andrea McSweeney here at Cytel, simply Andrea@cytel.com, and you'll see her direct line also on your screen. So please don't hesitate. Without further ado, Chris, we're going to have you get back online. And if you wouldn't mind, maybe start with Dave Whiteman's question about the CHED example and the coding of 0 versus 1.
Thanks, Mike. Dave Whiteman asks, for that CHED example, in other words, the corneal graft example, age was coded as 0 and 1, and he's asking, could some other coding have been used? Absolutely, but it turns out that in this case, because we only have 2 groups, that the substantive result of the inference would be exactly the same, regardless of how that was coded. We could code it as, 1 or 4 or 0 and 10 or whatever, but provided that we just have 2 groups, the p-value computation would actually turn out to be no different. That would change the values of the test statistics, but not the relative distribution in terms of their ranks. So thanks for that question. Also, I want to emphasize that what Mike said, that I did request that these data sets be made available to all those who attend. That would allow you to perhaps play around with them, yourselves, using code that you may have developed in-house, or using other software tools, just for the sake of comparison. As far as I know, I don't think there's not any major software package right now that has a module that provides permutation tests when the data are correlated.
And Chris, before you get into your next question, I noticed that some people saying they have trouble downloading the link, and that's because actually we just modified the link, and I'm going to share that with everybody right now. We inadvertently had an odd character, a percentage character. So as you continue, Chris, I'm reposting the direct link to today's slides for immediate download.
There's another question here from another attendee about whether these are available in SAS. The answer is yes, through Proc StatXact, which is the StatXact plugin to SAS. All of the procedures I've talked about today can be used in SAS as well, using that. that product. Another question here asked, could I provide the references for the permutation test discussed today? Absolutely. I think the way that I can do that is perhaps, well, I'll tell you one thing. Some of these references are contained in the user manual. The StatXact user manual for this module, the chapters that cover this module actually contain, a pretty good list of references. But what I can do is I can add some of these references on an extra slide for the future. I don't know if that is okay, Mike, but we can certainly add a bibliography slide.
Yeah, I don't see why not, Chris. It's a good idea.
Let me see. Another question that was asked, one about the capabilities of StatXact 10 beyond what's available, like say in SAS and R. I mean, I wouldn't say that we are, we're necessarily directly competing with SAS and R, at least StatXact is. I mean, StatXact, in my mind, has just kind of filled an important niche in the world of exact inference. And so, what I think what Cytel tries to do through its proc StatXact and proc logexact products is to provide an important complement to what's already out there. So as far as SAS goes, right now there's nothing that has been there's nothing that's been implemented by SAS that actually performs what it is that is being offered here in StatXact right now. But that's the reason why we offer these procedures through the proc StatXact packages, so that those who are SAS users can use these seamlessly, as part of their SAS package. As far as R goes, R is a vast world of packages that have been uploaded and programmed specifically by researchers around the world. My take is, just in my experience, that there are a lot of R packages that do permutational inference, but I haven't seen any that are actually any faster or more efficient than what StatXact provides. In fact, a lot of packages use a lot of the same underlying algorithms that we use for StatXact, but they were just programmed by individuals kind of on their own. So I guess I'd say, in terms of what I'm speaking about today, the big distinction is that this is something that's really unique that's in StatXact right now. I mean, I don't think anybody else has a comprehensive module that provides all these exact tests for tabulated data when you have correlation.
And Chris, if I could add, the latest versions of both StatXact and logexact, version 10, have the ability, the built-in capability to effectively run R scripts that you may have. So you can use your R scripts in conjunction with the StatXact and logexact capabilities, and actually effectively expand your use, and even, if you will, customize your use to run R scripts within StatXact and logexact.
Yeah, that's true. Which would allow you to use, some of these procedures within the R environment as well to cross over. Deborah Wiener asks, can you do sample size calculations for these correlated data methods? Not yet. That is something that we've talked about, and we certainly want to explore that. It's an interesting problem because one would obviously have to make some assumptions about the degree of correlation. But for people who work, especially in pharmaceuticals, where you have a lot of historical data from multi-site trials, it may be, that may be fairly reasonable to be able to estimate that. I will say this, though, that aside from tools that may help with study design, we do have an initiative in the works to provide exact conditional logistic regression. So in other words, to extend what we've put in StatXact to logexact to allow individuals to, say, compute odds ratios and confidence intervals in situations where data are correlated and you don't just want a p-value for a table or a stratified table, but you may want to account for additional covariates as well, as you would in the logistic regression setting. So that's something that we're kind of working on.
And Chris and Deborah, all those with us, certainly another reason to please stay with us as your input and your suggestions, again, are read by the software development team, the people behind StatXact and LogXact, and it's evidence, it's data for us in our decision making and what new capabilities would be particularly useful to StatXact and LogXact users.
One other question, an individual asked, can this exact test handle a hierarchical level of correlated categorical rather than one level? Not right now, but I think that is something else that we've talked about as well. I think there was a paper published about this, and to be honest, it may be the individual asking this question may be one of the authors on that paper. The name certainly looks familiar, but I noticed that there was a paper published, I think a couple of years ago, that extended the exact test that we developed to a hierarchical setting where you actually may have multiple levels of correlation. And so, if the demand is there, and certainly this question might indicate that it is, then that's something that we could also add in the long run.
And Chris, someone earlier asked about training in exact statistics, if not StatXact and or LogXact specifically, and outside of your classes at Utah State, we'd hardly recommend, I think, Chris, you'll join with me, we'd hardly recommend statistics.com. Peter Bruce and his colleagues have a long and an excellent reputation in helping people at all levels to better employ exact statistics. And we could not recommend them more highly. And by all means, please let them know if you do contact Peter and his colleagues at statistics.com that we sent you.
There's another question here that comes from David Brown. He asks, were data may derive from different centers, some of which may be somehow biased with respect to the others? Is there some facility to detect and highlight these anomalies within an exact context? Yeah, that's a really good question. I hadn't thought about that, but I think that that's an excellent point. The correlation arises from the fact, if we're talking about the context of multi-center trials, then the correlation arises from the fact that individuals within a particular center are going to be more alike than individuals across centers for environmental reasons or cultural or whatever. And so that's a good question. I guess I hope I'm understanding what you're asking, David. But it sounds like what we're asking is, what is the connection between possible bias at a center and that sort of clustering or that correlation? It would be an interesting research question, I think, and maybe I'll sick one of my master's students on this or something, but it would be an interesting research question to ask whether or not, bias that's bias present within centers can be overcome by simply accounting for the correlation. I'm not sure, but that's a good question.
Chris, is there anything else that you wanted to address before we wrap up today?
No, I think that's it. Unfortunately I have a meeting I have to be at in a few minutes here, and so this might be a good time to wrap it up.
Well, if the questions are a indication of the content in the presentation, your demonstration, then certainly I'd say this was a success, and it really wouldn't be possible without the folks who joined us today. And fielding the questions and the rapport is something that these WebEx webinar demonstrations, make it all the more valuable and interactive, and we learn as much, hopefully, as you do, our audience. So once again, I'd like to thank Chris from Utah State for his work today. I'd like to thank everyone, especially for joining us. And I hope you have a pleasant day. And again, please contact us specifically with questions about StatXact through Anja. And please stay online to complete the very brief survey. Again, it's very important to us to hear from you. Once again, thank you from Chris and myself, and good day to all.